welcome everyone to this session, the expression problem generalized by Tony Morris. Tony, we're glad you could join us today. So without any further delay, over to you, Tony.
Thank you very much. Hello, everybody. My name's Tony. I currently work for an airline called Qantas. I write in a programming language called Clojure. I write code in that programming language. I have been doing functional programming for a little over 20 years. Generally, when I'm writing proper software, I use Haskell. Like outside of work. I live in Brisbane, Australia, if we've never met before. I've attended functional Conf a few times in India, in Bangalore. And I missed the place. It's awesome heading over there and seeing you guys in person. I'll hope to do it again sometime soon. And I do have a second casual job as a flight instructor. I teach people to fly aeroplanes. And I did actually go to an airport in Bangalore a few years ago. I think it was called Jaipur Airport. And I tried to rent an aeroplane, but I did not succeed. That's just because my license is recognized in India, but not that day. Anyway, it would have been fun, but I do miss the place anyway. So I'm sitting here in my home office here in Brisbane, and I'm going to talk to you about the expression problem, and I'm going to generalize the problem, and I'm going to, once the problem is understood, talk about solutions to the problem, although I will not go into great detail about those solutions because I have talked about those before in the past. The goal of this talk is to lead up to those solutions and understanding why they are important. So in this talk, I do use a programming language syntax that I just made up. So hopefully you can recognize it. It's not really the point. The syntax is kind of beside the point. But hopefully you can understand the problem that's being described, and then we'll go through some solutions or what solutions would look like. So as mentioned, if you do have any questions, please send them in the chat. I will stop and answer that question. I'm watching the chat while I'm talking. So I'm going to tell you about the expression problem. Generalized. So why is it called the expression problem? Where did it come from? So Phil Wadler, quite some time ago, defined the expression problem. And to summarize it, it's to define a data type by cases. So for example, we might have a data type that is it's an integer or a string, and those cases being integer or string are the two cases. And we might want to add new cases to that data type and or new functions over that data type. And Phil Wadler said without changing existing code, like in the original memo. I think an important distinction to make there is what we mean or what he means by without changing existing code. It is not to do with whether or not we have to recompile it or whether it's interpreted like some programming languages are. It is to do with the fact that the existing code continues to work without us ever knowing or caring that some new case has been added. So hopefully that makes a little bit of sense. It's not about, changing the existing code dynamically or anything. It's about not changing it at all and not even caring that it even exists. It continues to work. So this is the expression problem. I will go into more detail about the definition because I think that's kind of key to making the point that I'd like to make. And also in that memo, Phil Wadler said that whether a programming language can solve the expression problem is a good indicator for its capacity for expression. Now, I think when I first learned about the expression problem and I first read this, which was quite a while ago, I didn't quite understand, I guess, the importance of that sentence. I firmly believe it today. And, the reason I believe it is because, like I said, I write Clojure code at work. There's thousands and thousands of lines of it. And in my humble opinion, almost all of that code is a consequence of poor capacity for expression of solving the expression problem. Or in other words, a lot of it is just code duplication, although it just doesn't look that way because of the way the language expresses a lot of its concepts. So throughout the years of writing code in Haskell and Clojure and whatever, I have come to this opinion that the expression problem is one of the biggest problems in our programming, in our everyday programming, and solving it well, or at least acknowledging it and coming up with a way to tackle it, is a pretty big component of our work. And I see this in code bases all the time. And one of my goals today is to convince you, or at least give you the tools to convince yourself that is correct. There is a big industry of just re-solving the expression problem over and over. And wouldn't it be nice if we didn't have to do that? So let's just give an example of what we mean by this definition. So yeah, again, this is just an invented syntax. But we have a data type here. And that data type is defined by, it's either an integer, which is the case is int, or it's a string, which is the case is string, or it carries no information, and we just call it just is. So this is an example of a data type defined by cases in our invented programming language. And I don't know why that it is commented out, but these slides are ultimately written in JavaScript, so that does not surprise me. But this actually is real code. And I'm just here on lines 5 to 8. So ignoring that, this is just a function called getInt, given the data type, and it returns an int. And what the code does is it says if it is the integer case in the data type, return 1 plus the integer. If it's a string, return 2 plus the length of the string, and if it's just is, return 3. And a key point about understanding the expression problem is we will call this a function over the data type. So this is a function. So given the data type definition, we now have a function over the data type. And if you've ever worked on any code base, someone comes along and says, hey, we don't just sell integers and strings anymore, we also sell booleans, or something like that. Or to be more succinct, we need to add a new case to our data type, and in this case, it's a bool. So we modify our code in our isBool code, our data type code with an isBool case, and we now ask the question, so looking at line 1 there, which prints out, so constructs the data type with the isBool case, and then calls getInt on it. We ask the question, what should that code do? Or in other words, what goes where those 3 dots are on line 4? Now, do we have to modify that function? Or what is it that what is a good principled software engineering approach to this thing that we've just done? So my experience, yours may be different. Feel free to add in other things that you have seen in code bases. But these are the first line defenses I have seen. Just simply throw an exception. If we call getInt with the isBull case, and if we remember the code, it doesn't handle the isBull case, in which case let's just throw an exception and crash the server, or whatever the consequences are of throwing that exception. Another one is to fail early on the getInt. So the compiler examines the getInt function, tells us that we're not handling the isBull case, and therefore fail the compiler. And another approach is to write, instead of adding in the isBull case to the data type, we write an entire new data type that has the additional case added to it. And yeah, this is throwing an exception at runtime. And I still do see this. It's 2025, and I think it's amazing that programmers try to convince themselves or try to convince me that, yes, that exception will never occur. Trust me. Now, you may not be as cynical as I am, but the moment I hear that, I am now certain that that's going to occur. That exception will be thrown. It's almost 100% indicator, is in my experience. So a false promise, from my perspective, it does not guard against this problem. Convincing ourselves that we're going to do this is the thing that makes us do it, in my experience. So yeah, failing to compile the original function, it is a robust solution. But if we took this approach, we modify the existing code, the getInt function, and we will add in, handle the isBull case, and return an integer. And it can be time consuming, right? Because although I've given an example of one function, getInt, I think it's important to imagine a million bazillion functions, as many as possible. And given that, we would have to modify all of those functions, or in other words, rewrite all the application. So this is what it would look like if we write a new data type. So we create a new data type, and we've got the previous data type as one of our cases, and we add in the Boolean case to our new data type. And this approach does seem to work. But if we continue to use this approach, we will end up with a lot of nesting, because once it comes time to now add yet another case, we would then have to add yet another data type, and so on. And so our original data type, our original integer, for example, is embedded deep down, deep down in the data type hierarchy. So implementing functions over this approach. So for example, we write a function over the Boolean, can quickly become clumsy as the nesting layers get deeper and deeper. I don't know about you guys, but I hear this a lot. This to me is very uncompelling. I don't quite have words for this other than that's just a lie. Yes, you do. Otherwise, why aren't you staying at home? Yes, you do change the code. Yeah, turn the types off, and that just defers the error. So it just allows you to go home and tell yourself that the code works for that day only. But this is the expression problem, or this is an example of the expression problem. So we have just run into it. with this trivial example. And I'm hoping you can extrapolate perhaps to real examples in your real code base, but they are everywhere. So this is the original expression problem that Phil Wadler described. And what I'm hoping to do is to talk about a more general problem, which includes this problem. Or in other words, generalize the expression problem. So this is an opinion of mine. Maybe you agree or not, but what would a solution look like? So in terms of, let's describe the solution. Well, however it is, whatever its concrete details are, what would it look like? So we would have a minimal interface for which the data type can express its components. So for example, we would have an interface that expresses the relationship between the data type and the integer, or the data type and the Boolean, and then an ability to write all functions over that data type in terms of that interface. Or in other words, all of the functions will not be specific to the data type because they will be written in terms of the interface. Now, this is a general principle of abstraction, right? Which is define the minimum definition. So, yeah. So apparently, Alexander's doing a talk on a solution to this problem tomorrow. That's cool because this problem is everywhere. So looking forward to that. But yeah, the general principle of abstraction is to minimize the interface, to give it the minimum requirements so that we can meet it, but not too small, such that we can maximize the amount of functions that we can derive from that interface. And a common example that I use to talk about this principle is we might talk about an interface that describes comparing two data types for equality. So given two things, return true or false, are they equal? We could put that in an interface. And then we might also have another interface which defines the ordering of two values. So whether given two values, whether they're less than, greater than, or equal to. And with those two interfaces, we can say that there's a relationship between them, which is to say that if you can define the ordering over two of those values, you can define the equality over those two values. And so given, for example, ordering, you could sort a list of those things into their ordering. So you wouldn't want to put anything more on that interface. That would be too much, or it's too big, because some data types may not meet that definition with the extra definition added to it. But from that interface, we can derive functions such as sorting a list. Given only equality in comparison, we cannot sort a list of those things. So we need some strength to the interface, but we don't want too much, such that we can derive the function sorting a list of those things. So that's an example of the principle of abstraction. But we want to apply that principle of abstraction to what any solution to the expression problem would look like. The same principle: minimal interface, maximized functions. And by maximized, I mean all functions, right? So we don't want to have to modify the getIt function. We don't want to have to modify any function. So given our previous example of a data type, I've just listed here some functions that we may want to write. And again, I've just listed 4 possible functions here. These 4 resemble all possible functions in what I'm trying to get to. I want to be able to write any function, but you'll see that each of these functions describes the data type. So whatever their implementation is, once we add in the new case, each of these functions would need to be modified as things currently stand. But we want to write an interface over which we can still write those functions. That's what the solution would look like. So, for example, uses the data type, is a constructor with that value there, return true or false. get the integer out of the data type, only if it has one, add 1 to the integer if it is an integer, but otherwise just leave it alone, or reverse the string in the data type if it is a string, otherwise leave it alone. So these are examples of functions over our example data type. But a solution, a solution would express itself not in terms of the data type, but each component. We want our interface to be minimal, and so that our future data types, or in other words, when we add cases, are able to implement it. Several solutions have been proposed. If you type it into Google, I could tell you my opinion about each of these, if you like. But Golang claims to solve it by the interface keyword. No, it doesn't. It does not minimize the interface with maximized functions. I assure you all the Golang programmers out there are solving the expression problem right now today. Similar for Ruby, closure def protocol, very similar again. It does not solve the expression problem. In other words, it does not express the minimal interface over which we can maximize our functions, all functions. Object algebras or tagless final, that's been around for a while now, maybe 10 or 15 years. And that's just a link to the original paper. And polymorphic variants, they've been around for even longer. So these are potential solutions. I'm going to talk about, or I'm not going to talk about because, like I said, I'm not going to go into any detail, but I'm going to suggest one solution. And then there's this solution. When I wrote these slides, I've probably been having a bad day at work writing closure. But one solution is just to turn all the types off, open the data type and hold it all in your head. Just create a math with a key and just add a new key or something like this. It's still a math. Hold all of that structure in your head. And why does our code keep crashing? So I do not propose this solution. I guess I'm lamenting that this is even suggested as a solution. It's not. I hope the reasons why are obvious. But yes, we could just make all of our code a map of string to string. This has a penalty associated with it. I hope that's obvious. It is not a good solution. Okay, so just to review our previous example of a data type. Pardon me. Our data type is an integer or a string or a unit value, or it's just is, right? Just is just doesn't have any data associated with it. We understand the expression problem to be when we need to add a case to our data type, and we would like our existing functions to continue as normal without having to touch them. And suppose those functions already exist in our code base. Pardon me, just have some water. And yeah, this is, I just wanted to put in something, I guess, a little bit more realistic. I can't see you, but if I said put up your hand if you are using JSON at work, I think most of you would put your hand up. Oh yeah, you can raise a hand. Okay, cool. Okay, I'm getting lots of notifications that hands are being raised. Cool. But yeah, so this is an example of a data type defined by cases over which, that is more realistic, right? So JSON is a number, or it's a Boolean, or it's a string, et cetera, et cetera. Now, this is where I want to get into generalizing the expression problem. And by that, I mean, like, now's a good time to pause and just make sure you are, you're on board with the expression problem is a thing. It exists. It happens. We encounter it. We deal with it. But this is not a data type defined by cases. This is a data type defined as an it and a string. It's not an int or a string, as in the previous example. It is just a typical record type, as you know, you might have to, I'm sure you use every day at work in your code. And similar to the previous example, although we're not defined in terms of cases, we now want to add not a case, but a field. We want to add a field to our data type, and we don't want our functions to change. That is, functions that use the person data type. And again, we could go through the same set of solutions. You know, we could have a map, and the map has two keys, an integer and a string. And then to add the Boolean, we just add a new key for the Boolean, and you know, everything keeps running just fine, except for the functions that don't handle the Boolean case. We just hope that we never call those. Or we could write yet another data type, wrap the person class as one of the fields, and add Boolean as another field. I was just fast forwarding then. So all of the same potential solutions exist for this problem, although this problem is not defined in terms of cases, the only difference being it's defined in terms of fields. We might have very similar functions over the data type. So given a person, return the integer, whatever it might actually be called. Add 1 to the integer in the person and return a new person, or reverse the string inside the person and return the person. And I have seen this a few times in real code. We're looking for that interface in order to abstract away the field inside the data type, right? So we would define an instance of hasInt for the person data type, and its getInt implementation will return the field, and similar for the string. And I think that's a good first approximation, but it does have a problem. And the problem is when it comes time to reversing a string, we need more than just getting the string. We also need to then reverse it, construct a new person, and return that. So that interface is minimal, but too small in order to write all of our functions. Again, we want to be able to write all of our functions. It's too small. So we can take this generalization even further again. We want to be able to write functions over this data type, person 2, where we add 1 to both int fields of the data type. And so I guess the point I'm trying to get to here is this. I think someone just raised their hand. But yeah, if there's a question, please feel free to type it in the chat. So yeah, we want to be able to add 1 to both int fields of the data type. In this, just as a particular example of a function over which we might want to write over the data type. And further again, if we have a look at this data type 2, again defined by cases, integer or a string, but in this case, it's or a person. Now, a person has fields. So what we have now is a data type defined by cases, and one of those cases is a data type defined by fields. And we might want to write the function which, given a data type 2, okay, I'm not sure I can see the Q&A window, that's all. I can see the chat window. Yeah, so this is a data type defined by cases where one of the cases is defined by fields. And the function we may want to write is given a data type 2, if it is a person, add 1 to each of its integer fields and return the new data type 2. And what I'm trying to do here is give you examples of functions over data types that I want to be able to write, or in other words, that interface must allow me to write that function that I just described and more, including those that I can't even think of right now. Okay, so let's just step back for a minute. So there's some relationships that that so far I'm just hand waved over. So a data type is either an int or it's something else, or a string from memory. A person is an int and it's something else. A data type 2 is 0 or many int, and a person 2 is 1 or many int, or in other words, 2. And the reason I've defined it that way is because that is important to the way that I'm going to talk about a solution. There is a relationship between these relationships. So, for example, given a data type is either an int or it's something else, a data type 2 is weaker than the relationship between data type. Yes, because actually I don't think that's correct. That's a mistake. Sorry. But the relationship between person 2 and int is weaker than that between a person and an int. Or in other words, a person has 1 or more ints, and a person 2 has 1 or many ints. That was like 2, 0, many. Actually, no, that is correct. Yeah. But there is a relationship between the relationships that we are describing between our data types and their cases and or fields. So this is a diagram of what we're trying to describe here, which is the relationship between a data type and an integer is stricter than the relationship between a data type 2 and an integer. And the relationship between person and integer is the same as the relationship as the person 2 and integer, which is stricter, again, than the relationship between data type 2 and integer. That strictness converges, or in other words, they are both stricter in the same way. So we would like an interface to express each of these relationships. We want that expression to be minimized in the definition of the interface, and we want the operations over that interface to be maximized. And my meaning for maximized here is to be able to write all functions, including those that I can't think of yet. Or another experiment is, given a proposed solution to the expression problem, if I can think of a function that I cannot write, then you have not solved it. Or in other words, I'm going to keep thinking of functions until I'm exhausted, in which case, hey, you might have a solution. But if I can think of one function that I cannot write, you have not solved it. But if we can do that, if we can meet these meanings for the expression problem, then we have solved it in the general case. We have solved it not just for cases, but also for fields, and we solved it for other possible relationships. So what is the name of these relationships? Now, I know some of you already know the answer to this question because you know my opinions, but if you didn't know my opinions, I will tell you the names. Those names are all types of optics, and the relationship between data type and an integer is called a prism. The relationship between a person and an integer is called a lens, and the relationship between data type 2 and integer is called traversal. So I guess one key takeaway is, if you had heard of this thing called optics or lenses and prisms and so on, what actually are they? They are interfaces that allow you to express these types of relationships between data, and then those interfaces allow you to then write functions across the data without necessarily having to change the data type itself. So this is what I think is a really good solution to the expression problem. It does, in fact, solve the expression problem. It is not without penalties. Even early this morning before work, I was writing Haskell, and I think I wrote like 700 lines worth of optics, and it was not very fun. I feel that there's probably a better way, but I was hacking it together. So they actually defining these are like the instances of the interface. Defining those instances can be a lot of work, but this is I still think that work is worth it for the benefit that you get, which is the ability to write any function across the data type now. So optics solve it. They define the minimal interface to express the relationships between data, and the derived operations are maximized, and that is we can write any function. Optics solve the expression problem in general. All right, so that's what I'm trying to say. They do. They solve it in general. There are other, I would say, solutions, although they all solutions that I have seen, those that actually solve the expression problem, look very similar. They all look similar. They're not. Some don't have the word optics in it, or they don't define it by optics, but they all look very similar. And so I'm starting to believe that whatever solution we end up with, or what our grandchildren will be using one day, will look something like optics or similar to solve this problem. So to summarize, a lens between A and B, the relationship between data type A and data type B, is that A has exactly one B and some other things. A prism has exactly one B or some other things, and a traversal has one or many B and or some other things. So this is a loose way of describing the different types of relationships. The expression problem originally described by Philip Wadler is solved only by prism. So he was talking about data types defined by cases, or in other words, when A has one B or some other things, and those other things are the other cases. In general, optics solve other types of relationships as well for the expression problem. That's everything I've got. These are just the links to the original papers for object algebras and polymorphic variants. So what I'm going to do now is I'm going to stop sharing my screen and see if I can find the Q&A window. The best way to implement optics in a language that has no support for monads, propunctus, et cetera, et cetera. I will type an answer, but I'll say it first. So yeah, I don't have one single answer to that question. I've written optics in Clojure, which I just took a completely different approach. There are no types, and so you can just pretend that you do have monads. The biggest problem I ran into is there's no support for type classes or dictionary parsing. So you don't have an implicit applicative part getting passed in. You have to pass in that applicative definition. And the way that I solved it in that case was to use the reader monad over the applicative instance. So that's how I would solve it. Pardon me, in a language that does not have types. When it does have types, like for example Java, I think there are two ways. One is to just turn the types off. Turn the types off, or use reflection. That's the same thing. And just do what I just said. And the other one is to just copy and paste code. Unfortunately, that's, one way is type safe, but you have to copy paste code. And the other way, you have the types turned off and it's pray and hope. I don't have a really good solution to that question. It's a really good question though. Or I guess another solution is just don't use that language. But, we have social pressures to use certain languages today, and that's just how things are. Solve society is one solution. Good luck. So yeah, on to the next question, 2025. Yeah, using AI to write the optics. That is not something I've thought about. And the reason I think that's a worth investigating is because there exist relationships between, as I am writing code, there can be the relationships between data types can quickly blow out, and it becomes unreasonable to write all of them. And therefore, which ones should I write is a question that I asked. So maybe the computer should write them as I need them, and it just knows that I need them. But yeah, that's a good question. Why not? Maybe because you haven't written the code yet. Maybe that's why not. So I don't really have a better answer than that. I think it's definitely worth investigating though.
Thank you, Tony, for sharing your experience.
Yeah, no, yeah, it's good fun. Yeah, thanks. And I hope to be in Bangalore sometime soon.